Good afternoon. I'm Steve Vio from StubHub, and this is PJ Pocarel, and we're going to be talking about how to sniff exceptions and accelerate your ability to find performance anomalies. Also joining us in the presentation will be yours, Kim. He's our ML architect that helped us get to the point. Let's click through these. So here's the agenda. How we built the exception sniffer, the process we went through, some of the use cases it addressed, how we use the Splunk machine learning toolkit, some of the enhanced use cases regarding smart alerts, and then a summary. So how many of you have used the StubHub website? Oh, wow. Wow. Lots of sports fans here. For those of you that don't know, StubHub is the world's most trusted secondary ticket market. We have buyers and sellers. We sell tickets for almost any kind of performance or sporting event. And it's an e-commerce site that has desktop, mobile, and MWeb products. So our stack. As you can see, this is just kind of a high-level snap. We have a distributed microservices architecture, most of it REST services. We have about 70 different pools of servers comprising of about 4,700 actual hosts and running about 1,000 microservices. So when something goes wrong, it gets a little complex, and deciphering what's going on and going through the exception stream that occurs when there is a failure is difficult. So what's an exception sniffer? When we were in ops and working with the QA department, we decided to make this tool. And it was about 3 or 4 years ago when we came up with the concept. But what we did is basically make a tool that basically it's kind of like Splunk inverted. In other words, all the bad stuff, all the bad errors, all your 400s, all your 500s, anything that's causing a problem. I wanted visibility to that. And kind of not seeing the good stuff like the 200 log lines and stuff like that. So we wanted to be able to track errors, we wanted to be able to trend errors, and we wanted to be able to see if something changed and what the impact was. So we decided to make something called the Exception Sniffer. The types of errors we focused on were 2 types, mainly Java errors, being that most of our services are in Java, and business errors. They're kind of 2 distinct categories. Your Java errors are coming out of what your heap and your Java layer is saying, and your business errors are also logged from your application developers saying that this field is missing or a business process failed of some sort. So Exception Sniffer, version 1, made it about 3 years ago. It's pretty prehistoric. We started with the Splunk REST API, and we'd go grab a chunk of exceptions in an interval like every 5 minutes, and then we'd put it into a database that we had created. And we categorized the errors if it was a database error, or if it was a connection error, or if it was some other type of error, and put them into kind of our own self-made categories. We used our own alerting manager to send out the alerts, and there was no machine learning. It worked. It was useful when we had releases and things went wrong, but we didn't have any machine learning on it, so it was kind of, there's still a lot of humanistic determination we had to make. And then the data started to grow. So first month ran fine. About month 4, noticing querying the data became extremely hard. We had to kind of archive the data, and eventually the tool, reporting-wise, was very time-consuming. And while it did work, there was a decent amount of maintenance we had to do to it. So enter Exception Sniffer version 2. We decided to rebuild the tool, and we decided to make it better. First thing we did is we built it all in Splunk. The second thing that really made the difference for us was we ended up using the metric store. And the metric store allowed us to save the data in a very fast manner and query the data and trend the data. We also used the Splunk dashboard components, and we also used their alerting mechanism. Basically, we were lucky that we were able to iterate and make a better tool. So for our use cases, what we wanted is we wanted some deep insights into application errors when failures occurred. We wanted to know what the root cause of them. We wanted to be able to trend them from month to month, year to date. Much of our traffic is very seasonal based on events, World Series, Super Bowl. We wanted to be able to go back and trend these data and see if there were differences between months, weeks, depending on what was happening on the site. We also wanted smarter alerting. Most of our alerting was pretty much determined by ourselves. There was no machine learning involved, so we wanted to use machine learning to alert us. And we wanted to be able to search through the data really fast, like run a monthly report in a matter of minutes than a matter of watching things summarize in a really slow way with the old tool. Last thing is we wanted whitelist functionality. In other words, having the most current, most fatal error bubble up to the top so that the ops team would be able to see that there was a problem right away. So I'm going to pass this off to PJ, and he's going to go through the journey and how we built the tool.
Thanks, Steve. So we started very simple, with index equals Java and exception. So this actually just gave us all the Java log lines that have exceptions on them. And then we just added the Java exception field, which is like an auto-extracted field in Splunk. And that just gave us all the exception types for that we're looking for. Next thing, we added some so in this case, we just added stats count. So we wanted to group our exceptions by, so we grouped them by role, which, like Steve mentioned earlier, just our instance groups that we have, and then pod, which are our individual data, our data centers, and then the Java exception type. So at the end of this query, what we got was just a list of Java exception type, role, pod, and then the data center where it was happening. So it didn't take us that long to create this first basic query. But soon we realized, all right, the queries are giving us results back, but it's taken very long time to run. And we found that, especially when we were running, the weekly and monthly reports, then the query performance was even much more slower. And the next thing was, these data were only retained for 30 days, so we lost some historical context, and we did not have enough data to make a good model when we wanted to use this data for machine learning. All right, so at that point, we got together with Joris and our Splunk admin, and we wanted to see, all right, what are some of the solutions that Splunk has that can help us? And there was a couple of different options. Summary index is one of them in Splunk. We decided to go with the Splunk metric. It seemed very straightforward to set up. What we did was, since we already had the raw events in our logs, we did the log to metric conversion. And there's other ways to get data in metrics, but in our use case, we just did the log to metric conversion. Two commands that we used, mcollect and then mstats. Those were the commands that we used. Mcollect to get the data into our new index called metrics, and then mstats to query that data. So as you can see here, this is very obvious. We know that metrics you get better performance, but at the same time, we were seeing huge improvement in the query response time. So here, just an example, same workload that we ran against the raw logs and then on the metrics, 6 seconds versus 3 seconds. So you can see this was a huge performance improvement for us, especially when we were creating these weekly reports. We didn't have to spend hours trying to get that data back. So this was a big performance improvement for us. And this opened a lot of possibilities. We were able to use this data to create dashboards, views, reports trending for alerts, and then for anomaly detection. And I'm going to talk about these topics in the coming slides here. All right, what you see here is our dashboard. This is the first thing that we built. This has Just a basic view of our data. On the top, we have different dimensions that you can see. I don't know how to get the pointer. Anyway, the top row is the pod role exception name and the last 24 hours, whatever day you filter it out by, and then just different views of the data. And then finally, like on the bottom, there is the Java exception, which is just a list of exception, and towards the end we have another column. We created this column called the drill down, and this basically just takes that search and creates another search that will take you to the event logs. And this has been a very, very useful feature for us because now, whenever we have a production issue, we can just click on the drill down. It'll take us to the exact message when we have that exception, and we're able to see the call stack from there and easily do the RCA. Next one was our weekly report. So this is a report that we start sending out once we have the data in the metrics index. What you see here is a percentage daily trend of exceptions day by day for last 7 days. And on this column is the roles, our instance groups, where these exceptions are getting logged. So this is how this data is presented. We send this every Monday morning. We have a dashboard that we built for this report, and we use the scheduled PDF report functionality. Very easy thing for us to do. It just sends that email report for us. Now, previously, we were taking this report, consuming them. We had a mail client built in. It was a Java application. Now we just use Splunk entirely and let all the the scheduling, everything, let Splunk handle all of that. On the last report, you saw the error percentage. One thing I just wanted to quickly mention was we were trying to figure out how we can calculate that error percentage, and we were the problem we ran into is that we had the exception metric there, but there was no other references to calculate the error percentage. So we found a tstats command, which is pretty handy. I don't know how many of you have used tstats. Show of hands. Okay, there's a couple of people. So this was the first time I used tstats as a part of this project, and I think it was pretty useful for us. I just wanted to throw that over there. And then building on the report, the last thing we did was do the monthly report. What you see here on the top are just bars, different sizes. These are just month-to-month total aggregate exception count for a particular month. And then on the bottom, we have exception count by different roles. We have top 6 very high volume roles. Those are roles that we report here. And this report, it actually, it's a monthly report, and it's helped us just generate some awareness about performance. Before we started sending this report, a lot of times the developers, error metric and exception metric was not really a thing that people were tracking. So with this report, we were able to show them that, hey, we're looking at these errors and exceptions, so make sure these are not over their normal trends. All right, so the reports were great. They gave us a lot of information, but we also needed data in real time to take action. We are not going to stare at the dashboard all day, so we needed to create some alerts. And that's where our next phase of building this tool was to see what type of alert we can create with this metrics data. And I'll pivot a little bit here just to explain what we saw in our data. We did a quick exploratory data analysis because one of the goal of our team, we're in the performance operations team. So our goal was we don't want to go through all these 70 roles, create these different alert policies, and maintain those alert policies, right? It'd just be too much things for us to do. So we decided, how can we just create some blanket alert policy, just few alert policies that can help us notify whenever something critical happens. So that's why we started looking at the data, and we saw very interesting patterns here. We saw there was a lot of high and low values. Some server groups, you'd see exceptions, then there's no exceptions happening. And then same data, different patterns. We also found that we're normally logging 40 million logging events per minute, and we have about 11 million exceptions a day. And that includes both the Java exception and also our custom exceptions. So there's quite a lot of data there. So once we did that, we played around with the MLTK toolkit, used the k-means to find out, do some clustering of our data to see how we can group these different server groups in. And we came up with 3 different patterns or groups. The first pattern here is, as you can see on the bars here, like these roles constantly have exceptions that are happening all the time. These are mostly like brokers and seller-related errors. For example, some broker would send us API calls that would have bad rows or listings or whatever, or sometimes it's just an authentication issue. So in that case, you would see a lot of these exceptions. And on these roles, the exception is greater than 1,000 exceptions per minute on average, and there is some seasonality. Like you can see, there's a little bit, this was taken at 10 a.m., so there's some seasonality there, but this is not, we found that this is not really seasonal. Like for example, if we're looking at our site load or especially the site load, then we see that that shows a little bit more seasonal pattern. But in this case, we saw that this is, the pattern didn't look that much like a seasonal pattern. And the next group of servers, we have about 50 instance groups that show this type of pattern where it's greater than 100, less than 1,000. There's a large variance. So you can see like the first bar here to my left, that has like very small count, but then you have these higher bars. So these are, again, roles that have exceptions, and we found that these are mostly like page controllers, ancillary roles, our batch services, not directly related to client traffic, but just some secondary roles that we have. And this is our favorite pattern, pattern 3. So have no exceptions. So very easy to set up alert policies. We can just say, hey, if you see an exception on these roles, send me an alert. Right? So these are very, very easy. We have there is close to about 20 server groups, about 500 servers. We don't have any exceptions on them. All right, so with that in mind, the first alert policy that we created was the new exceptions alert policy. And our goal was, how can we find new stuff when there's always these other ongoing stuff happening? So we created this alert, and it's divided into 2 parts. So first part is we use a scheduled job that writes exceptions for that day, and it uses the output lookup command and saves that to a CSV file. That's the first part of the alert. The second one is we have alert job that runs every 15 minutes, then does a comparative diff, checks if that alert there is, if it saw that alert there yesterday. In that case, if it saw there yesterday, then notify us. So that's the new exception alert. The next one with similar type of design is the critical exceptions alert. So these are things that we know are really bad, that if something happens, if we see these exceptions, then the server is probably down. For example, Java lang, out of memory error, stack overflow error. So we have a list of exceptions that we created we know those are bad exceptions. We save them to a CSV file. Then we have alert job that runs every 15 minutes. It uses the input lookup command, which just creates a new set. It compares that set with the previous set, and then we get, if there is something that it finds that's part of the critical exceptions, then we get notified. All right, I know there's a lot of alerts, a lot of talking about alerts. Finally, the last one that we created is the threshold, alerts based on threshold method. So we wanted to look at how we can use Splunk to do some of the learning for us using machine learning toolkit. We started playing around with the standard deviation method because we understood that well, just based on our previous experience. We knew with standard deviation, you could just say, if something is 4x the standard deviation plus average, send us an alert. we started playing with that, and we realized, hey, this data, the anomaly that it detects depends on what method you're using. So for example, if you're using standard deviation versus standard deviation sliding window, it's actually detecting different anomalies for you. And also if you're using median absolute deviation, we saw it's totally different anomalies that it's detecting. And then finally, we tried the probability density function, which is another anomaly detection function. And we found that that actually works best for us, and we'll talk a little bit about that towards the end here. But probability density function was easier for us to set up. It supports the fit and apply command, so you don't need to save something to a file. You can just use those two commands. With that in mind, I'm going to invite Joris, who's going to give us a little bit intro about the threshold method and using some of the ML that we use for our project. Here we go.
Great, thank you. First and foremost, before we get into the next set of slides, one thing I do want to mention, the most important part of this is the data, right? It's not the algorithm, it's the data. The fact that StubHub was struggling with trying to build ML models with only 30 days of retention, and yet leveraging the summary indexing allows them to now retain a lot more history of data to give you more context or give the algorithm a lot more context in what they're doing. Having said that, what I wanted to do is give you guys a little bit of intuition and just a little bit of flavor around what we actually implemented and why density function, this algorithm that PJ mentioned, is actually a very powerful algorithm to potentially leverage for outlier detection or anomaly detection. And of course, that being sort of what's behind the smart alerts that they're actually creating. If you're familiar with the machine learning toolkit, we do currently have an assistant called the Numeric outlier detection within the machine learning toolkit. And this is where StubHub started their journey when they looked at trying to detect outliers. And again, these charts are kind of to give you some intuition around what's actually going on. So if you sort of get started, if you were to do this today yourself, you have some sort of a numerical value over time that you want to detect outliers. You can simply put that into your search in the Numeric outlier detection assistant, and then select your thresholding method, whether it's standard deviation, median absolute deviation, or interquartile range. And as you can see here, this is sort of a sample of a data similar to what StubHub saw with one of the different types of data that they had. We can easily find the global outliers, and you can sort of visualize that, okay, we have this data that's sort of seasonal over time. Great, we found some outliers. But if you kind of dig a little bit deeper in the observation of the data, you can see that there are other outliers in here that completely go unnoticed. And primarily because in this simple sort of approach, we're kind of almost stupidly or simply kind of saying, just take all the data and figure it out. So, okay, great. We found some outliers, but we want to be a little smarter. How do we detect those outliers that are sort of in between? And that's where, again, using that numerical outlier detection assistant, you can then leverage the sliding window mechanism. Using the sliding window, all of a sudden, wow, we found a bunch more outliers. And if you kind of look at the number to the right, we went from about 40-ish outliers to now 149. And quite frankly, yes, it did find those outliers that we sort of saw from the previous slide that got undetected, but it's also probably a little bit too noisy. So what's the right threshold we select? Do we set a standard deviation? Do we up that number? Do we decrease it, sort of depending on what you see? And if you can look carefully at this chart, you'll even see like at certain periods of time, the shading is representing the actual window of what's considered to be normal. And when you actually have a huge outlier, that window either gets too large for that period following an outlier that actually happens, or if your data is very normal, that window gets super small. So this, again, becomes an approach that often becomes a little bit too noisy. So trying this again, we further test using median absolute deviation. At first observation, you can see that the windows kind of look a little bit better, but look to the right, it's even noisier. Why is that? What's going on? What's happening? Why are we having trouble detecting outliers using these very common statistical approaches that pretty much every product out there has available when they say they have machine learning, including our own? And the intuition behind that is understanding the shape of your data. And what I would always recommend before you do any sort of outlier detection is see what your data looks like as a histogram. And that's what we're looking at here. That same data set that we just looked at in the last 3 charts is a histogram. We do have a macro in the machine learning toolkit called histogram that you can leverage. Go ahead and take a look in our docs to find more information about how to use it. Or if you know sort of the commands to create a histogram, you can do that as well. But what I've done here is I've overlaid the normal or sort of Gaussian curve or bell curve, however you kind of understand that, to see how the data would be interpreted by simply using average and standard deviation. And as you can see, average is not average. The average is actually 1 standard deviation, sort of to the right, or the mode actually, 1 standard deviation to the right and 1.5 standard deviations to the left. And quite frankly, if I were to observe this data myself, I'd say 2 standard deviations is probably where I'd kind of land on where there should be outliers. But then you try a different data set, and the shape of that data changes. So really the question becomes, can we build a diagram or sort of this line that truly fits our data? That's really sort of the question that we're trying to answer. And really what it is yes, you can, using the density function algorithm. By simply calling the fit density function, what this does is this is effectively fitting the shape of your data into the specific distribution that it calls, and then you can easily apply that model that is learned using the apply after you sort of set the into clause and name the model that you have. The other perspective, exploring your data is very important. So make sure you sort of understand, and density function is a unique algorithm within the machine learning toolkit that you can actually use a by clause. You can split your data. And here this chart is just sort of diagramming, looking at that same data set as a box plot. So what's sort of the distribution of the data per every 3rd hour? I would have actually shown every hour, but the box plot got a little bit too small, so I just chose to go every 3rd hour. And you can see that the median and sort of the extents of the data every 3rd hour, this would actually be sort of a nice almost sinusoidal curve if I showed every hour as well, is different. So why not split our data, so fit density function again, by date hour? That also sort of gives you another perspective around your data that becomes important. Sorry, that's where we have it here. And what the diagram or the table that you see there is an example of the output that we see when we save this model and look at the summary of the model using the summary command. You can see the date hour showing on the left column and the different sort of mean values and effectively a different type of distribution that's understood. I wish I could do a lot more treatment to the density function, and I'll kind of talk about that shortly, but more importantly, what I did want to sort of highlight to you is this: we did this work with StubHub through our machine learning advisory program. And I do want to sort of let you know that this is a service that is available to you complementary with your Splunk Enterprise or Cloud license. What it is you're basically getting help from Splunk, where we will bring the data science expertise to your use case. You can also get early access to machine learning features where applicable. And it also is an opportunity to share your results, as we've done here with StubHub, around your success with your machine learning use case. If you're interested, you can contact us through mlprogram@splunk.com. And sort of talking to not being able to do a full treatment of density function, because quite frankly, I could probably talk about it for hours, we do have some other sessions that are leveraging the same algorithm. Another session that I'm presenting with one of our principal engineers that's worked on the algorithm in itself tomorrow with the session FN 1213, and there's a couple others that are highlighted where they've actually applied that use case or applied that algorithm to the use case that they have. So if you have different sorts of pivots on this algorithm that you like to sort of hear stories around, you can do that. And with that, let me turn it back over to Steve.
Thank you, Euros. So we learned quite a bit along the way here. Comparing the threshold method versus the density function, there are some pros and cons. The threshold method, obviously it works, and it's easy to understand, but ultimately we found for outlier detection that the density function was much more effective. Almost every site has some type of hourly trend, depending on when the traffic is the highest and when it's the lowest. The probability function handled that really well, and we also have strange broker traffic, so we might have guys that come in at 8 p.m. And it's very laborious threshold method-wise to go through all of it and set thresholds. It just takes a long time. So we found the PDF function to be amazing and saved us a ton of time. In the effective alerts, going back to our patterns again, these are how we applied and solved the problem. For pattern 3, which is like the 0 exception, we used the diff alert and a basic static threshold. For pattern 2, which were the medium ongoing exceptions, we used the diff alert and the probability density function. And then for pattern 1, we used the diff method and the probability, just the diff method, excuse me. So how did tracking exceptions help us? Well, we were able to find duplicate exceptions. We were able to find exceptions that had no meaning, and we were able to reduce our exception count by 50%. Ideally, you want your logging to mean something, and if you're in the ops capacity, you can't rewrite the logs for everyone. So you have to find a way to actually, either thin them out or tell the teams that this message is being logged in duplicate, or it's a stack trace, or it's meaningless. Can we remove it? Basically, cut down the noise so that you can find the real stuff. And this is really what we were able to do. We also found, a list of culprits that were, usually the high generating exception roles, which we can target and mark for further improvement. So it kind of made an improvement plan for us. And that ultimately, our alerts were accurate. They were modeled. They were modeled every hour. They weren't, it wasn't something that we had determined, but the toolkit had determined. So there was a reliability to the alerts now that other ops members appreciated and benefited from. There's nothing like an alert that comes across that's a false positive, and everyone's going crazy, and then you just go, oh, wow, never mind. It's super irritating. So what did we really learn? As every metric you look at, every data set you look at it, you want to look at it from different angles. You want to histogram it out. You want to look at 95th percentile. You want to look at the median. You want to look at the 25th percentile. You want to look at it all because it does tell you something. It's telling you something. You may not think it's important at the time, but it is definitely telling you something if you take the time to take it apart. And that's what we were able to do with Joris's help. And it wasn't something that you're going to do in 2 or 3 days. It's something you're going to have to strategically focus on and apply. But the learnings were basically really know your data set. I mean, take it apart. Many tools, there's a whole showcase of tools in there. Just give you the average or 90 percentile. What's in the 95th percentile? These types of things. Always keep asking questions. What we ended up finding is that the data was rather complex. Every pool had a different time it would get exceptions. Every pool interacted differently. And ultimately, if you can clean up the noise, then your servers aren't logging just nonsense and context switching and slowing down to do it. They're actually giving you some meaning when they log something. So this is pretty much what we learned along the way. And it was interesting because we all had seen the data before. We all had seen the data for years in most cases. And we kind of thought we knew it pretty well. Come to find, you put some machine learning on it, all of a sudden you have a different view into it. So I'd like to open it up for some questions.
Yes, your PDF function, how often you model it, how often you update the model, we change it, things like that.
I'll pass that off to PJ.
So our experiments, like the one that we recently did, on that we do it every week. So we just retrain, we run the model every week, and then just use the fit command that just saves it to the model. Yeah. So it's a weekly cycle right now, but we are still, we are getting effective alerts right now. We are planning to experiment further, see if we can change that duration for longer time, see what happens. But right now it's 1 week period. Yes.
So you just said, right, Java exception can have different timestamps. It can have a different weight. It can have a different stack trace altogether.
Yeah, right. That's a great question. Actually, we thought about that initially to save the stack trace, but soon realized that the stack trace can be like really long, several lines. So right now, what we're doing is for a role, we just save the name of the role, which is like a server, just say, for example, role, and then the data center where it happens, and just the signature of that. And from that, most 90% of time for us, it's always going to lead to that same call stack that we see. But yeah, we initially thought about that because we had one extra step needed, but right now we don't have that. Yeah.
Anybody else?
I think there was.
Yeah, so the question is around understanding the distributions that we have and what happens if it doesn't fit. So effectively, kind of going a little bit into the theory, at its core, there are three distributions we understand and how we try to fit. The first one is we try to understand the normal distribution because, quite frankly, it happens. I personally, in a lot of the customer interactions I've worked with, I haven't seen IT or security data fit normal very well. Or almost never, like I've seen any data fit normal distribution. The second one, which I find more common, but actually isn't always selected by us, is the exponential distribution, which is basically ones are good and big numbers are bad, right? So think like number of logins that happen, right? Or amount of data transfer, perhaps, or whatever it might be, right? Small numbers are good, big numbers are bad, at a very sort of simple perspective, or often called like a F distribution as well. So that's one we understand. And then third is what's called Gaussian Kde. There's a lot more sort of theory behind it, but Kde stands for kernel density estimation. And what we're doing is we're customizing the fit of curve. So based on what we saw with the previous slide where I showed a very interesting sort of distribution of data, we're actually fitting almost exactly what that looks like. So every Gaussian Kde fit is actually unique to that data set in itself. So that's kind of where KDE allows us to have very custom sort of views around the data. And that's typically, I would say, a majority of times you find that the chosen algorithm or chosen distribution is the KDE one that we have. But we select from those three, find the best fit. We have sort of different things that happen automatically. Or if you want to force fit, or even say take one data set and run it against all three yourself, and look at the outliers in all three sort of contexts, you can do that. So there's a lot of customization that's available, but at a very high level, the KDE gives you the ability to have very sort of custom views on the data.
I think there was one question.
So when you were showing us the threshold set to 1.1, my question is, it looks like you reduce the number of outliers to the satisfaction level by putting into a distribution around those. Do you have any pointers or methods around setting that correct threshold value? Or is it entirely just trying to have?
Yeah, so a question around like setting the right threshold. Like in the screenshot, I showed a threshold, I think 0.01 was, and that's actually the default. If you don't set the threshold, our default is 0.01, which quite frankly, in my opinion, in a lot of my experience, is a little high. What I sort of recommend to customers typically is start with 0.005, so 0.5%. If you sort of think to normal distribution, the normal distribution, if you think 3 standard deviations, because we're kind of used to using standard deviations, or a lot of us are, the assumption there is 0.3%, but in actuality, 0.15 or 0.14% of the upper, because a lot of times, a lot of use cases are just looking at the upper threshold versus the lower, because lower often are negative numbers and we don't care. So 0.15%, kind of use that almost as a measure of your confidence based on your intuition of understanding the normal distribution. But even from there, I would say 0.5% or 0.005 is a good place to start. And often even a decent sort of place to land if you kind of want to be sort of a very simple, let's just set a threshold and let it run for a few weeks. And then from there, that's kind of where you can actually further optimize it. And the beauty of the threshold actually is you can do it at the apply step. The function doesn't change. The actual distribution stays the same. But if you said, let's run it for a couple days, it's too noisy, let's change the threshold on day 3, even though we don't rebuild the model. So that's something that you can easily sort of tune on the fly if that's something you want to do. Back over there.
How do you triage when something goes out of family like that? So you get an event, you based off of not being curved density function. So where do you go from there?
Do you mean like how do we triage the issue? It's our workflow. So for these alerts, the new exceptions alerts and critical exception alerts, we've subscribed the operations team on it. So they get notified, the NOC team gets notified for that. And there is some like subjective thing that we have to look at. Sometimes it's not clear if some exception is actually just causing some API or pages to go down. But generally, we look at the exception if the count is greater than 1,000. 1,000 is like our high side. So if count is greater than 1,000, we know there is a problem. And then we just follow our normal workflow, NOC, ops, to triage it.
Yeah, the other thing I'll kind of add there is there's a lot of context you can add to it. So like the summary command example that I showed, it's showing you what's normal, right? What's the mean, what's the min and the max in the data that it trained on. So if you want to add that to the context to say, we found an outlier. Okay, great. What do I do, or how do I contextualize that? The summary command, you can sort of join that data. That's sort of a useful way to make sure you have context around that data if you've never seen that data before, especially to say, well, based on what we trained, this is what's normal. And so that's at least that first level of determination you can make to say, is this useful? Because if it's right at sort of the cusp of the data you train, you might say, well, yeah, it's, according to the math, an outlier, but it's not that significant for me to expend energy on right now if I have other outliers that are identified at the same time.
How do you handle the seasonality of the depending on the climate or change or something, or based on traffic, some weather pattern may come, pattern may come, some critical event may test like the last exam.
So one of the things that we recently added for the same issue that you mentioned, we were getting a lot of counts for our exceptions, and when we looked at the actual logs, we found that these were happening, for example, on our inactive pod, which is not even running any, not serving site traffic. So one of the things we recently added is a status of where the traffic is. So we add that flag at the end of the column just saying, this is the active pod. You should be seeing the exception at this rate on the active pod. This is not an inactive like stage environment. So on the active pod, if we see some exception gets flagged 1,000, some exception count is 1,000, then we know that all right, this is something we need to look at. And again, next 15 minutes, because this alert runs on every 15 minutes. So next 15 minutes, if we see the same thing, then we know that there is some pattern, something that needs to be investigated.
Yeah, and one other thing I'll also add is knowing your data is important, right? The math doesn't lie, but it might not be what you're looking for, right? And so the context there is that, what if the data is seasonal? Well, take seasonality into account with the split by clause. That's a really sort of easy perspective to do. Yeah. Split it by hour, or maybe the seasonality you're looking for is weekday versus weekend. Create a feature to identify weekday versus weekend. Or maybe you're looking at, sort of work hours versus non-work hours. Or maybe if you're a financial company and you have sort of really sort of interesting patterns based on sort of market events, right? Make sure you sort of understand open and close of market, right? Those types of things, being able to classify that in your data and then use that as a way to split by, all of a sudden gives you very unique distributions of your data based on the knowledge that you have on your data. And that's sort of important, is as much knowledge as you're adding to the front end to say, find me the outliers in the context that I already know, that gives you a lot better and more useful alert or outlier sort of that's found than just simply saying, find me some outliers. So the split by clause gives you sort of that ability to customize as you see fit, and you can run multiple fits sort of on the same data if you want to split, let's say, based on weekday versus weekend versus per hour versus type of user or server group. That you can sort of go crazy, and typically people kind of will pivot on that data in multiple ways.
Hope that answers your question. Yes.
In the back.
So speaking of seasonality, you're looking at weekend, you're looking at weekdays. What happens when you have a holiday? How does the model account for that?
So right now, our model doesn't account for that. That's a good point. We do our day of the or hour of the day is one thing we use, and then the day of the week. So those two are different dimensions that we create the models by. We're not accounting like holidays because for us, we're like our traffic pattern throughout the year is pretty much the same. It's not like big retail shops how during Thanksgiving or something you might get huge traffic. So for that reason, so far like we haven't seen any issues with that. But we do want to add some of those things, like just exclude some days, for example, when we had huge issues on the site, for example. So those are some things that we are still experimenting with.
I mean, if you have the ability to store your metrics, the other thing that you can do is go back last year and find out when was your highest session count month, and know these things in advance. Now they're not going to land on the same exact day the next year, but you know when the hot time is coming. I mean, we don't necessarily have like like Black Monday or these fire sales, but World Series is pretty popular. So we expect high demand coming in World Series, and if there's a high demand week where our model learned the week before that wasn't high demand, you're going to have to understand that there could be something that it won't catch. But in hindsight, if you could train for the whole year and apply that and it was accurate, then you would know that, hey, September, end of September, middle of October, World Series. People are going to be jumping around, people are going to be moving tickets, people are going to want to be looking at a lot of games, lots of customer traffic, lots of broker traffic. So again, it goes back to knowing the data. I thought I knew the data well because we've tracked it and I've had reports for several years and other tools, and this really opened my eyes. Just seeing the different views that you can get from the machine learning. I was like, wow, no. The human eye can't grab all that detail. But you can, you're going to have to make some decisions about what would be the best way to stay out of trouble. And that would be like knowing your high traffic times, understanding, maybe learning, like you said, having a model just for high demand situations where you can see where most things interact in a certain way. Because we do have on sales and stuff like that, and the pattern is completely different.
I know we're a couple minutes over here, so I just want to thank you for those who have stuck around to the end. If you have additional questions, I think we'll be here for another few minutes. Happy to answer questions, but thank you for your time.
Thank you.
Thanks, Preston.